Section 6 of Chapter 1 deals with complex numbers, so we're going to go through some new things that you probably haven't seen before. You may in the past have wondered, why do we keep talking about real numbers? What other kind of numbers are there? Well, we're going to start working in this section with imaginary numbers. So prior to now, you've been working almost exclusively or exclusively in the realm of real numbers, and now we're also going to add a new set of numbers, imaginary numbers, which also include complex numbers. So key vocabulary that you're going to need from this section, the imaginary unit I, we're going to talk about that. What is a complex number? What is an imaginary number? Complex conjugates, that's really, it sounds so complicated, but it's conjugates like we've looked at before, but they're dealing with complex numbers. The complex plane, so we're going to graph complex numbers, and we're going to find the absolute value of a complex number. So the key idea is that we have this imaginary unit I, which is equal to the square root of -1, I. A complex number would have a combination of imaginary numbers and real numbers, so something like 3 plus 2i is a complex number. So 2i is an imaginary number. A complex number combines real numbers with imaginary numbers. Complex conjugates we'll talk about, but they're conjugates like everything else. For instance, the conjugate of 3 plus 2i is 3 minus 2i. The complex plane has real numbers horizontally and imaginary numbers vertically instead of x and y. And then we have the absolute value of a complex number, which is essentially the Pythagorean theorem with a couple of wrinkles. So when we get to that, you should be able to recognize that it is derivative of the Pythagorean theorem. So types of work that we might do with imaginary numbers would be calculating resistance. You can see that for different types of items in a parallel circuit, so this is a parallel circuit, which allows more than one pathway for electricity flow. So this gets into the land of electricity and electrical engineering. So we can look at the idea of what the effects of resistors, inductors, and capacitors are and measuring the impedance of a circuit. So we'll do that at the end. And in the meantime, we'll move on and we'll learn a little bit here about imaginary and complex numbers. So if r is a positive real number, then the square root of -r is equal to I times the square root of r. So for example, the square root of -3 is equal to I times root 3. So if you think about how that happens, here's what we're really doing. Remembering what I already told you, that I is equal to the square root of -1, and taking what we've already learned about the properties of radicals before, we know that we can factor radicals somewhat like this. So if I had the square root of -3, that's equal to the square root of -1 times the square root of 3. So I factored the negative out of -3 by factoring out -1. And I know that I is equal to the square root of -1, so that would be equal to I root 3. Okay, so if we want to put that into practice, for me to solve for x in this particular problem, I'd want to take the square root of either side. So x would be equal to plus or minus the square root of -28. If I want to simplify this, I know that -28 is the square root of -1 times the square root of 4, so I factored out a perfect square, times the square root of 7, which is a prime number, so this will be fully simplified when I'm done. So this would be plus or minus, square root of 4 is 2, I root 7. Okay, so the only thing really new is this idea that if I factor a -1 out of the radical, then I can simplify that square root of -1 to be I. Everything else is the same work we were doing when we were solving by taking square roots and simplifying radicals. So if another item on this is that if, right, the square root, if I is equal to the square root of negative 1, then I squared would be equal to the square root of negative 1 squared. Well, anytime I square a square root, the result is the radicand, and in this case the radicand is negative 1. So I squared, this is another interesting idea, is that I squared is equal to negative 1. So I, the imaginary unit I, is the only thing that you can square and get a negative result. So in practice in a problem, if I start to simplify this, I'll subtract 2t squared, so I'll get 4t squared, and I see that I don't have any middle terms, so I'm just going to go ahead and put my constants on the other side by subtracting 5. So I subtracted 2t squared from either side, and I subtracted 5 from either side, and this is what I have. Then I'm going to divide by 4, and then I'm going to go ahead and take the square root. So t would be equal to plus or minus the square root of negative 1, so that would be plus or minus I. Okay, so again, one new wrinkle, and that's the concept that we can factor out this negative 1. Okay, when we start working with complex numbers, as I mentioned in the introduction, complex number in standard form is a number a plus bi, where a and b are real numbers, right? A is the real part of the complex number, and the term bi is the imaginary part. So you have a real part and an imaginary part. Okay, so as long as b is not equal to 0, right, which would make the I drop out if it equaled 0, right, then it's going to be an imaginary number. And if a is equal to 0 and b is not 0, that means I wouldn't have a real part. That would be a pure imaginary number, right? So if you don't have the real part, it's an imaginary number. If you don't have the imaginary part, it's just a real number. And it's a complex number when you have both parts. Okay, so I think I've said the same thing several times now. And when we work with these items, it ends up, the imaginary part of it ends up working a lot like a variable. The I sort of functions a lot like using a variable like x or y or something like that. Okay, so moving on into some level of practice with that. If I want to add complex numbers, this really is no different than if I had this. Sorry, for x, right? So this, when I'm saying it can act a lot like an x, that's really what's sort of going on. So I have 6 plus 5, that's 11. And I have negative 3i plus positive 4i, that's 1i. So this should be very familiar to you in terms of adding complex numbers. It's the same skills you've already had in adding binomials. Negative 1 minus 7 is negative 8. And 1i minus negative 5i is plus 6i. Okay, so you're still going to follow the same rules that you've already used with combining binomials. Okay, so in this case, the I doesn't really work functionally any different than if it were a variable. Okay, now a same deal if we were going to multiply. The distributive property still applies, but then we'll have some extra simplifying to do at the end. And let's see how that works. So I have minus I times 4 is minus 4i. And minus I times minus 8i is plus 8i squared. So again, it worked a lot like if I had a variable. You would have gotten negative 4x, and you would have gotten plus 8x squared. So very, very similar. What's different, though, is that I know I can simplify I squared because I squared is equal to negative 1. So when I substitute the negative 1 in, I'll end up with negative 8 over here. And now the way we write complex numbers is the real part first. So the real part is negative 8 minus 4i. So real part first and the imaginary part last. Okay, so that's multiplying. The only thing new is that when I end up with I squared, I can convert it to be -1 and move on and simplify. Okay, so that means that I'm never going to have I in my equation to any power higher than the first power. Because if it's any power higher than that, then there's still simplification to be done. So if you have I to the second power or third power or fourth power, you still have to continue to simplify. Okay, again, I'm going to use FOIL now to multiply these two together. And we notice they're the same except the signs are changed in the middle. These are what are called conjugates. Okay, and conjugates are really important to some of the skills we're going to work on in a minute. Because if you watch what happens when we do this problem, conjugates solve a challenge for us in a way that can't be solved any other way. So if I use FOIL to multiply, 8 times 8 is 64, and 8 times 3i is 24i, and -3i times 8 is -24i, and -3i times +3i is -9i squared. And you see how the middle terms drop out. So the i's to the first power all went away. So I end up with 64 minus 9i squared. So I should have already known that anyway, because conjugates create the difference of two squares. So I know that from special patterns, a plus b times a minus b is equal to a squared minus b squared. So a in this case was 8. So when I simplified, I got 8 squared, which was 64. And it's going to be minus b, right? B in this case was 3i. So when I square 3i, I get 9i squared. So I could have gone straight to this instead of doing FOIL. And now, as I finish up, I have 64 minus 9 times -1, because I squared is equal to -1. So this becomes 64 plus 9, which is equal to 73. So you'll notice I started off by multiplying two complex numbers together, and by the time I'm done simplifying, I have one real number. Okay, and this is very important because just like we can't have irrational numbers in the denominator of a fraction, as we've already learned that, we need to acknowledge that because I is equal to the square root of -1, it is an irrational number. So I can't have I in the denominator of a fraction. So when I have a complex number in the denominator of a fraction, how do I get rid of it and simplify? I multiply it by its conjugate, which we'll go ahead and we'll practice here. Okay, so we've seen this before, right? When we studied radicals and rationalizing denominators when they were radicals. Now we're doing it when the denominators are complex numbers. So if I want to get rid of I in the denominator of my fraction, I have to multiply by the conjugate, which is the same binomial with the sign change, because these are conjugates and they create the difference of two squares. So this will be 2 squared, which is 4, minus 3i squared, which would be 9i squared. Now if I do that to the denominator, I have to do the same thing to the numerator, right? If you remember, this fraction has to equal 1. So my numerator and my denominator always have to be the same. I'll use FOIL to multiply this all out to create the numerator. 7 times 2 is 14. 7 times 3i is 21i. 4i times 2 is 8i. I need a bigger numerator. And 4i times 3i is 12i squared. Okay, now I need to simplify my I squareds, and I need to combine like terms, and then I'll be fully simplified. So in my denominator, I'm going to have 4 minus -9, right? Because I squared is -1, 9 times -1. So my denominator is going to become 13. In the numerator, I'll have my 14. 21i and 8i is plus 29i. And then plus 12 times -1, right? I squared is -1, so that's minus 12. 14 minus 12 is 2 plus 29i over 13. So you'll see now I started with a complex number in the denominator, and by multiplying by the conjugate, I'm able to eventually have a real number in the denominator, which is what I need to have. Okay, so this is rationalizing the denominator when the denominator is a complex number. Okay, to give you another example now, right, this is 3 times the square root of -1, basically, right? So I'm going to multiply by the square root of -1, which is I. Right? So to write out what I just mentioned, that's what I is equal to. If I want to get rid of this radical, I don't have to worry about the 3. I need to get rid of the radical. I'm going to multiply by itself, which is I. Okay, so when we multiply through, I'll have negative 2I minus 5I squared. That was a terrible I. And 3I times I is 3I squared. And then in simplifying the I squareds, I'll still have minus 2I, but I'll have minus -5, that's plus 5, over 3 times -1, which is -3. And the last thing I have to do is rewrite my numerator to be in the correct order. So it's going to be 5 minus 2I over 3, and I'm going to put the negative on the outside. Okay, it could end up being anywhere, right? Okay, plotting complex numbers is pretty simple. As I mentioned in the introduction, the vertical axis, which we're used to being the y-axis, becomes the imaginary axis. And the horizontal axis, which we're used to being x, becomes the real axis. And what I do is I plot my real number horizontally. I move by my real number horizontally and by my imaginary coefficient vertically. So I would do 1, 2, 3, 4, 5, and then down 5. 1, 2, 3, 4, 5. And this is the plot, right? So I went down 5I and 5, and the location that matches that is right here. Okay, so that's how I plot complex numbers. Pretty simple. It's a lot like plotting ordered pairs. It's just you're interpreting this complex number and you're selecting the parts out of it that you're going to use. Okay, if I do that again, minus 5, 1, 2, 3, 4, 5, and up 3, 1, 2, 3, this is that place, right? So this distance here is 3I, and this is -5, just like we're used to. Okay. Now, if you take a look at finding the absolute value of a complex number, so you look how we graphed it. We did the real dimension here, and then the imaginary dimension in this direction. And when we look at the absolute value, it's this distance here. So we can find the absolute value of the imaginary number. It's the distance from the origin to its location on the graph. And we can use what is essentially the Pythagorean theorem to solve for that. Okay, so again, I'm working, you'll notice I'm not working with I, right? I'm working with the coefficients involved, the real number and the coefficient from the imaginary number. So here I could say the absolute value of z, so we're using z as the absolute value of the complex number, right? Absolute value of z is equal to the square root of the real number squared, 10 squared, plus the coefficient from the imaginary number squared, which would be the square root of 100 plus 49. Remember, when I square -7, -7 times -7 is positive 49. Okay, so this is equal to root 149. And then I would want to simplify that if possible. Okay, I'm looking at 149. I don't believe that I have any perfect squares that are factors of that, so I believe this is fully simplified. Okay, if I'm just looking at 4I, right, that has 0 for its real component. This is a pure imaginary number. So the absolute value of z in this case would be equal to the square root of 0 squared plus 4 squared, right? Which would be equal to the square root of 16, but pretty obviously that's going to be 4, right? And that makes sense when you think about how that would graph. So if I just sketch that really quick, 1, 2, 3, 4. When I don't have the other component, I don't have a diagonal line. Like here I have a diagonal line, so we need a formula to calculate that out. But you can see very quickly that the distance from the origin to this point is 1, 2, 3, 4. Okay, so you could have solved that either way. I happen to use this, but it's pretty obviously algorithmic that it's always going to be this answer. If you have a pure imaginary number, the absolute value of that imaginary number is going to be the coefficient. Okay, now let's go through working on our electrical problem. Okay, so we have this formula for calculating impedance for a parallel circuit which has more than one pathway through. So you can see you can go through this way, and you can also go through that way, right? So there are two different ways to go through. And if I can calculate that using this formula, but I have to create the values in order to do that for Z1 and Z2. But I've got this example here that will help me, right? So first I want to figure out what that is. What is Z1? So if you look here, I have a resistor and I have an inductor. Okay, and what they tell me is for the resistor or the impedance, but we want the impedance, right? So we're taking a look at that. It's just going to be the number for the resistor, but for the inductor, it's the number times I. So it's going to create this, it's going to create an imaginary number, right, when we get through that. Right? We actually add them up, so it's going to create a complex number. So this would be 4 plus 5I. Okay, now if we look at Z2, we need to add these up. So again, we have a resistor, so that's just going to be 7. But then we have this capacitor, and you see the capacitor is this number, the 3 ohms times I. So it's minus 3I. Okay, so what I've done is I've used my little chart to take these two pathways and calculate their impedance, right? And now for the whole parallel circuit, we know that Z will be equal to Z1, which is this item, 4 plus 5I, times Z2, which would be 7 minus 3I, all over Z1 plus Z2. Okay, and as we go through simplifying this, I'm probably going to have to extend the page a little bit. When I multiply these guys out, I'll get 28 minus 12I plus 35I minus 15I squared in the numerator. And in the denominator, I'll have 4 plus 7, which is 11, and I'll have 5 plus negative 3, which is minus 2I. Okay, continuing to simplify, I'm going to ignore the denominator for the time being, but you can see I have to rationalize this denominator, so there's going to be a pretty chunky step still to come. Okay, so when I combine like terms, I'm going to have 28 minus 12 plus 35 is plus 23I. Minus 15I squared becomes plus 15 because it's minus negative 15. Right? So I'm just going to continue. The denominator didn't change. We're going to come over here underneath this little chart here now. And so 28 plus 15 is 43 plus 23I all over 11 minus 2I. And now I would need to rationalize the denominator. I'll multiply by the conjugate, 11 plus 2I. And then we're going to go ahead and multiply these guys out and simplify. Okay, so let's make a little barrier here. 11 times 43 would be 473. And then 23i times 11 would be 253i. And 43 times 2i is plus 86i. And 23i times 2i is 46i squared. I'm running out of space. So sorry, that's a big mess. Let me move that over. Oops. Let me move that over and write it so you can read that a little better. 46i squared. In the denominator, it's a little simpler, right? We're going to have 11 squared minus 2i squared because I'm going to create the difference of two squares. So that's going to be 121 minus 4i squared. Here we go again. Long problem, right? The nice part is the denominator is going to be very simple. This is going to be 121 minus negative 4, so that's plus 4. That's 125. Okay, up here, I'm going to have the 473 minus 46. So that's going to be 427. And then 253 plus 86 is 339i. Okay, so this ends up being the total impedance of this particular circuit. Okay, so one of the things we practiced everything regarding complex numbers almost in this one problem. So we multiplied complex numbers, we added complex numbers, then we simplified using I squared, then we rationalized denominators. So this problem may have taken a long time to do and had a lot of steps, but this problem basically reviewed, we did almost everything but graphing complex numbers right here in working with this one problem. Okay, so great problem for you to look at in preparing for the quiz.